between a diagram and a pattern that you usually explain?
Yeah, that's ad hoc terminology of my own design to simplify the combinatorics. A pattern is a class of diagrams that differ from each other only by a permutation of the indices on the vertices.
And could you define what you mean by components of a pattern?
Components of a pattern are components of a diagram. I mean the normal topological sense. Given a pattern of points with lines connecting them, two points are said to be in the same component if there are lines connecting them, and to be in different components if there are not. Okay? Component equals piece.
Okay. Could you define what you meant by O of D? And
O of D is the operator associated with the diagram D.
And in the discussion of Model 1, where you had that interaction Hamiltonian G, D, rho, you claim if rho is equal to 0, but if rho is not equal to 0 and its Fourier transform vanishes, where rho equals u squared, it makes mesons one at a time.
No, I said that on that case, if I said that, it was a slip of the tongue. I said that if the Fourier transform of rho vanishes on the mass shell, there is no amplitude for making mesons, even though the Fourier transform may be non-vanishing in other regions of four-dimensional K-space. I said we could understand that physically by looking at the structure of the diagrams, which we could interpret as saying that mesons were made one at a time. If we had had an interaction like rho phi squared, okay, then we would have had diagrams like this. Okay, two phi's coming to a single vertex. And then we would not have found such a corresponding restriction. Okay, because you could add the two momenta of these produced mesons together to make practically anything in Fourier space. It would not be just the value on the mass shell that would be relevant. Yes, Kay. No, first, did I answer your questions? Kay?
In the example you did where you solved that particular model, is there also another connected diagram that consists of nothing at all that corresponds to the number 1?
Yes, but we do not represent that diagrammatically. By convention, we do not. There is always a one term in the expansion of the exponential, and we do not represent that diagrammatically. It is always.
But does that also count when you take the exponential with the sum of connected diagrams?
No, because 1 is the exponential of 0, not the exponential of 1. It is not counted among the connected diagrams.
Oh, okay.
Okay. That's easy to see. If there were no interaction at all, there would be no connected diagrams by my convention, but not by the one you have suggested. And the S matrix would be the exponential of 0, which is 1, and the correct answer.
Oh.
Okay, is that a satisfactory answer?
That's fine.
Yes, sir.
Have you assumed rho to be real?
Yes, I always assume rho to be real, so the Hamiltonian is Hermitian. Yes, sir.
Why do you identify the phi fields of mesons and the psi fields of
That's purely a nomenclatural convention which I establish out of perversity in order to, because the structure is similar to that arises in meson-nucleon theory, where the Yukawa interaction is psi bar is now a spinor field, which in principle you know nothing about at this moment. Gamma 5 is a 4x4 Dirac matrix. Phi. Therefore, I call the psi's nucleons and the phi's mesons. Of course, in our, which is obviously parallel in the sort of diagrams you will get in their combinatoric structure, if not in their detailed algebraic structure with this sort of interaction. Also, the similarity is that the nucleons carry a charge and the mesons don't. Could be a theory of protons and pi mesons, for example. All right, I just needed a name for those two kinds of particles. I could have called them psi particles and phi particles, since after we work out the theory of fields carrying spin, we will have a lot to talk about, a lot to say about this theory. I use nomenclature that makes coming events cast their shadows before them. Yes, sir.
you explain what you mean by the symmetry number with the diagram?
Yeah. Symmetry number. The symmetry number is the number of permutations of the indices that leaves the diagram unchanged. Okay? In general, if we have n factorial ways of permuting the indices for a diagram with n vertices. Okay? But those do not lead to independent diagrams. We overcount by the symmetry number. Therefore, when we sum over all the diagrams of the same pattern, 1 over n factorial is replaced by 1 over the symmetry number. Okay. We will see later this lecture that when we get to Feynman diagrams, when we start assigning momenta to the external lines and telling what mesons or nucleons or antinucleons they create or annihilate, the symmetry number in this theory disappears. The 1 over n factorial will be completely canceled. This is not universal, though, and is, well, when I get to it, I'll make remarks about it. Yes, sir. Which problem? Dilatations, yeah. Yeah, the theory of dilatations is important in certain fields in high-energy physics. There is always an idea that if we go to very high energies, the fact that particles have masses should be unimportant in a very rough sense. And therefore, everything should behave as if the theory was massless. All the particles were massless, and massless field theories do possess dilatation invariance. Of course, the sentences I have just issued represent a pious hope rather than an actual program, and there are all sorts of complications that involve objects with strange names like the renormalization group that we may get to in the second semester of this course that turn that pious hope into an actual program. But although things get much more complicated, when you consider real interacting field theories, the theory of scale transformations does have physical consequences. Okay. Kay.
Yeah, one more question. When you talked about Wick's theorem, which expresses the time-ordered product and some other stuff, now there's also some theorem about a time-ordered product and normal-ordered products, and don't you really need that for what we're doing?
No, we don't need it for what we're doing. Of course, one can establish such a theorem. If you have a bunch, if your interaction Hamiltonian was normal-ordered, ours is not.
Oh.
Okay. Then, of course, you would have a time-ordered product of normal-ordered products. And then it's easy to see that you simply ignore contractions within the blocks that have already been normal-ordered when writing down Wick's theorem. However, we will not normal-order our interaction Hamiltonian, and I will talk. We will eventually have to face the consequences of doing that, but at the moment we don't need that generalization of Wick's theorem, that rather trivial generalization of Wick's theorem, I should say.
Not even in Model 3?
Not even in Model 3, no. We will consider diagrams like this. I will get to them at the beginning of next lecture. Whether
Okay.
yes, sir.
Is the scaling in that problem then to do with flattening out the cross-sections that were high energy?
No. It turns out that high-energy cross-sections, you can't, the masses are important. There's a scale of masses that is important. The energy is high, but the momentum transfer is small. And the momentum transfer is a number with dimensions of a mass, and it's typically on the order of well, in the forward direction is 0. And it's typically on the order of, within the forward peak is typically on the order of a pion or a nucleon mass. So we certainly cannot neglect the scale of masses in studying scattering cross-sections at high energies. We might be able to neglect masses when studying scattering cross-sections at high energies and fixed angles, because then the momentum transfer and the energy are both becoming large. But that's a disputed point at the moment in high energy theory. That is an unresolved point, whether the masses are important in that regime or not. As we say in the jargon of the trade, that people disagree about whether behavior in that region is scaling dominated, which means you can neglect the masses, or Reggie dominated, which means you can't. Okay. If there are no more questions, by the way, I like a lot of questions. This lecture began well. If there are no more questions, I'd like to first finish up some computations I was planning to do at the end of the last lecture, but due to the pressure of time and exhaustion, I didn't get to do, still on Model 1, and then turn to Model 2, and eventually, if we have time, to Model 3. I'll just write down some equations we had from last lecture. F of k is minus ig 2 pi to the 3/2 square root of 2 omega k rho of k and omega k. Alpha is integral d cubed k f squared. The n particle wave function for the final state, starting off from the vacuum, is a product of uncorrelated f of k's. And the probability of finding n particles in the final state is 1 over n factorial, times e to the minus alpha over 2, times a phase, which we didn't keep track of and didn't bother to compute, is 1 over n factorial e to the minus alpha to the nth, a Poisson distribution. Now, we can compute not just the, we computed that. That was our last computation, last lecture. And we can also compute the expectation value. That is to say, we computed also the average number of particles in the final state, which we found was just alpha. I would now like to complete, for the moment, my analysis of this model. We'll return to it later and find out some other things about it, by computing the average energy produced in this process, where you start off in the vacuum state and wiggle around the scalar source, and then turn it off and see how many mesons are left. The average energy, the expectation value of the Hamiltonian in the final state, is, of course, sum on n, psi n squared, integral, d cubed k1, dot, 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 d cubed kn, times the energy of the particles, to wit, omega k1 plus dot, 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 omega kn. And, of course, so we don't overcount states, 1 over n factorial. Otherwise, we would be counting the state k1, k2, and the state k2, k1 twice, and that is a bad thing to do because they're the same state. Now, this can be simplified because everything is symmetric. We can just as well write this as the sum on n, integral d cubed k1, d cubed kn, simply one of the omegas, say omega k1. The others obviously give n equal contributions, so I thus have 1 over n minus 1 factorial. Since this term is 0, when n equals 0, I could just as well write the summation as n minus 1 equals 0 to infinity. This is a term with n equals 0, does not. Yes, indeed there should be. I am terribly sorry. The integral is now trivial to do. N minus 1 of the integrals give us alpha. So I obtain sum n minus 1 equals 0 to infinity, alpha to the n minus 1 over n minus 1 factorial. I still have the normalization factor, e to the minus alpha, and the remaining integral gives us integral d cubed k1, which I'll just call k, f of k quantity squared, omega sub k. Of course, the summation is nothing but a fancy way of writing 1. So we have a very simple expression for the mean energy emitted in our process. It is simply d cubed k f of k squared times omega k. The mean momentum can be obtained by an identical computation with k's replacing omegas, and that is equal to integral d cubed k f of k squared k. This is the computation I didn't have time to do at the end of last lecture, and it completes for the moment our analysis of Model 1. Are there any questions?
Are there any conditions on rho in this model?
I always assume that rho, unless rho is nice enough to justify all manipulations we want to make. If you wish, it's a test function in the Schwartz space S. That is to say, it goes to 0 at infinity faster than any inverse polynomial and is infinitely differentiable.
I'm asking about the physics, not so much about that. I want to know, is there a time limit on how long you can jiggle?
No, as long as you stop jiggling eventually. Okay, eventually could be t equals 1 billion years. Okay, as long as rho disappears eventually. I don't care how long it stays on. I mean, of course, I can only do my experiment and say, are there mesons around after rho has stopped jiggling? Now I turn to Model 2. Model 2, I remind you, is exactly the same as Model 1, except that rho is now time independent, and therefore to fit it into our somewhat clumsy formulation of scattering theory, we have to insert a by-hand turning on and off function equals f of t g rho of x phi of x. This is, of course, an interaction picture phi, but I suppressed the i's on the fields. F of t, I remind you, is a function which I can plot. I'll put in some times. T over 2 I should write to keep consistent. This should be symmetric, although I may not have drawn it that way. It's 0 up to here, then it slowly rises to the value 1, and it keeps the value 1, then it goes down to 0 in a way that is supposed to be symmetric. And this point here is 1. Now, there's a peculiar thing that happens in this model that shows us we have been a bit too sanguine about the harmlessness of an adiabatic turning on and off function. If we compute the S matrix using our formula, we find that terms that depend on, there are terms that do not go away, that depend on the length of the time length. God, that sentence is getting confused. Let me reformulate it. We would find, if we were doing naive calculation, that there would be terms that depend on the time capital T in a non-trivial way and which do not go to constants as capital T goes to infinity. Let me explain the physics of why that should happen, and then I will tell you how to cure it, and then we will solve the model by summing up the diagrams. Let's, in the Schrödinger picture, make a plot of what happens to the ground state of the theory. Well, let me introduce some notation first. We use the notation 0 to represent the ground state of the non-interacting theory. Therefore, H0 on 0 equals 0. Of course, the real physical theory also has a ground state that is not liable to be 0. The theory not with the adiabatic turning on and off function, but just with this extra term added to its Hamiltonian. I'll call that 0 physical, the actual physical ground state, the ground state of the interacting system without an f of t, or t equals 0 if you will. That will have some energy which need not be 0. You know, generally when we add an interaction term to a Hamiltonian, not only does the ground state wave function change, but the ground state energy also changes. So it'll have some energy which I will call E0. Now let's make a plot of what we expect to go on in time, and what we expect the Schrödinger state to be. Well, we begin at the beginning of time, or up to the time minus t over 2 minus delta. Nothing has happened. We start out with the ground state of the non-interacting theory. And it stays that way because the Hamiltonian is the non-interacting Hamiltonian. It doesn't even acquire a phase because its energy is 0. We now turn on the interaction and get to time minus t over 2. Well, delta is supposed to be a very large time, although not so large as capital T, and we are turning on the interaction very slowly. And therefore, by the adiabatic theorem, explained to you in detail, I hope, in non-relativistic quantum mechanics, we expect the ground state of the non-interacting system to smoothly move into the ground state of the interacting system, because delta is supposed to be a very large number. Therefore, we will get the physical vacuum after we've done turning on the interaction. Of course, I haven't established any phase conventions for this state, so we might get it with some phase, which I will write simply as either minus I gamma minus, where gamma minus is some number depending on what it is, what phase it comes out with, and what phase our phase convention is for the physical vacuum. Now between minus t over 2 and t over 2, the system is is evolving in time according to the full interacting Hamiltonian. We turned on the interaction with full strength. This is an eigenstate of the full interacting Hamiltonian, so therefore it develops a phase depending on its energy, and when we get to the time plus t over 2, we still have e to the minus I gamma minus, e to the minus I E naught capital T, the elapsed time, 0 physical. Now we go to the time t over 2 plus delta, and again the adiabatic hypothesis takes hold, aside from a numerical phase factor, depending on the details of how we've turned the interaction on and off. I get, which I'll call gamma plus, I simply get e to the minus I gamma plus gamma minus plus E naught T times the non-interacting vacuum state, the bare vacuum as we sometimes say, again. Okay, this is a straightforward computation in the Schrödinger picture using the adiabatic theorem of non-relativistic quantum mechanics, which, if we're lucky, should be true in this instance. Are there any questions about the, that's why they provide us with lecterns for lectures of this sort. Are there any questions about this computation? Yes, sir. Well, I just said the adiabatic theorem tells me that the ground state of the non-interacting system turns into the ground state of the interacting system times some phase. And the phase in general, if you look up adiabatic approximation and shift, depends on the details of how the interaction has been turned on. Okay? Yes, sir. I've chosen them to be equal intervals. That's just for convenience. They could be different. Gamma plus and gamma minus. Oh, they should be, well, yeah, I suppose they're conjugates or something. It doesn't matter. I can look it up in Schiff and find out, but I mean, I just don't know. They might cancel each other out, but I don't think so by time reversal. Or they might be equal to each other by time reversal. I'm not sure. I think they're equal to each other by time reversal. Yeah. Yeah, they're equal. They're equal. Time reversal says the S matrix is equal to the time evolution matrix is equal to the one with the initial and final states switched, not conjugate to the one. They're equal. Now, writing this in terms of the U matrix, the time evolution matrix, we find vacuum, U of infinity minus infinity, vacuum equals e to the minus I, gamma plus gamma minus plus E naught t. Because that's the inner product between the Schrodinger state at time minus infinity and the Schrodinger state at time plus infinity. And I see I have, since that's on the left, I wrote a mistake there. I hope it doesn't lead to a mistake later on. If so, I will be very embarrassed. No, I'm sorry. The minus was right. The minus is right. I'm sorry. U of infinity minus infinity acting on vacuum is the state at plus infinity. Now, since we have a theorem that tells us that U sub I of t and 0 is e to the minus I h naught t, U of t and 0, and by complex conjugate, by taking the adjoint, ui of 0 and t equals U of 0 and t e to the plus I h naught t. We see, writing U of minus infinity, infinity minus infinity as U of infinity 0 and U of minus infinity 0, that this thing is also equal to, since the 0 is an eigenstate of h naught with eigenvalue 0, ui of infinity minus infinity 0. Now, this is just dumb, because we said we were going to turn things on and off, and this was going to be the S matrix element between the initial state and the final state. And this is certainly not true that in the theory without the artificially introduced f of t, that this can't possibly be the S matrix element between the initial ground state and the final ground state. The initial, in the real theory, without the f of t, there's no way of defining capital T, so you can hardly get an answer that depends on capital T. Indeed, the sensible way to define this S matrix element is to say it's 1. Because you start out, there's your static source with no mesons coming in. It just lies there like a lump. At the end of time, there are no mesons coming out. Therefore, we have obtained a spurious phase factor in this analysis, and the right-hand board shows the origin of that spurious phase factor. It's because when I was waving my hands and saying, well, when you turn on the interaction, it doesn't really matter because you're turning it on slowly and things are adiabatically going from the free particle states to the corresponding in states. I forgot about phases. They can develop phases. And if we have an energy mismatch between the energy eigenstate of the exact theory and the corresponding energy eigenstate of the interacting theory, then we will get a spurious phase factor, as we have seen. Now, there's a very simple way of getting rid of the spurious phase factor and getting a correct theory. That method is obtained by adding an extra term to our interaction Hamiltonian called a counter term. I will eliminate the phase factor for the ground state and then worry about whether there are corresponding spurious phase factors for the other states of the theory. I write d cubed x, rho of x, phi of x and t. Sorry, I did it, well, I'll put the f of t later. G minus a number I will call little a. F of t. Little a is a new extra term I have added to the Hamiltonian. It's just a number. And it is called a counter term because it is designed to counteract our error. I will choose little a so that the phase factor is completely canceled. That is to say, this adds a term which is, aside from a minus sign, f of t times a. A is just a constant, not time dependent. I will choose little a so that this equals gamma plus gamma minus plus E naught t. Then the phase introduced by the presence of the constant term little a in our S matrix element will be exactly canceled out, will exactly cancel the phase we have found here. In other words, I choose little a. Another way of saying that I choose little a is that I choose little a such as to force vacuum ui of infinity minus infinity vacuum equals 1. This is the equation that determines the counter term. Thus, little a is not a free constant, and I do not have to go beyond the scattering perturbation theory I have developed until now to compute it. I can just compute it self-consistently, order by order in perturbation theory, by composing this equation. Okay. So I've added a new term to the Hamiltonian to take care of our error in mismatching the ground state energies, and I can determine what that new term is strictly within the context of the perturbation theory for the U matrix, simply by imposing, to whatever order in computation or whatever approximation I am doing, this condition, which obviously fixes little a. Of course, we can also compute little a then as a byblow of our computation of the S matrix, and that's interesting because in the limit t goes to infinity, the term here that grows with large T is a times capital T, plus terms that are of order delta, which I don't keep because I'm going to this limit, plus terms of order delta, which I don't keep. And therefore, little a, my counter term, is identified with E naught in the limit of large capital T. So as a byblow of this, if I happen to be actually interested in a numerical value of the ground state energy, I can compute it because I know what little a is. And little a is in the limit of large T equal to the ground state energy. Okay? Is the general argument clear? So we've done two things with this counter term. We have eliminated our error in mismatching the phases, mismatching the energies for the ground state, and we have found a way in context using the U matrix of computing the ground state energy, if we are interested in computing the ground state energy. So it's a good thing to do. It cures our disease and gives us a bonus in addition. Now, in particular case of Model 2, once we have matched the ground state energies for the interacting and non-interacting system, in fact, this is obvious because just as it says, you add a constant to the interacting Hamiltonian, so its ground state energy is 0. Once we have cured our disease of mismatching the energies for the ground state, there should be no problems for the other states of the theory, because all the other states presumably consist of 1, 2, 3, 4, etc. meson wave packets impinging on rho. And if we go to the very far past, those states are away from rho and therefore should have add exactly as much to the energy as they would in a free field theory. Of course, we don't expect this to happen in Model 3. In Model 3, the particles are interacting even when they are far away from rho. There is no rho, in fact, and even when they are far away from each other. And in that case, we should expect there to be energy mismatch for the states with real mesons in them, as well as for just the ground state. However, in this case, knock on wood, we expect that this will take care of all the phase factors caused by energy mismatch. If it doesn't, we'll discover it soon enough, because I will now explicitly compute the S matrix, and if it indeed involves terms that don't go to constants of large T going to infinity, I will know that confident statement was wrong. Okay? So, I mean, I can never if I'm actually going to do calculations, I can never make a mistake in this sort of discussion, because when I do the calculation, I'll find there is something I have forgotten. Okay, are there any questions about the general thing? Now we do the computation. I know everyone gets uncomfortable when I give general arguments. We've been trained for years that if it's an equation, you just swallow it, but if it involves words, you don't understand it. But please, so if there are any questions, please ask questions.
Is the reason why you made a general argument because this would be renormalization?
Yeah, we're going to get there. We're going to talk about renormalization in half an hour. Or at least part of it. We won't get to wave function and charge renormalization for a few weeks, but we'll talk about mass renormalization. So, we have our Hamiltonian. We have the condition that fixes little a, and we remember that in the large T limit, little a, large capital T limit, little a is E naught, and you have a question.
Before A, you included the phase factor did you have to include those phase factors?
Gamma plus and gamma minus? Yeah, in principle, yes. There's no harm in doing it. A goes to E naught. Whether I include them or not, A goes to E naught as T goes to capital infinity. As capital T goes to infinity. So I might as well include them and make this strictly 0 for any f of t, not just 0 in some limit. Now, we now have 3 connected Feynman diagrams. We have our 2 old Feynman diagrams, exactly the same as in the previous model. This one, which is just a number, and a number we will compute shortly. Feynman diagrams, Wick diagrams. This one here, which we talked about before. And now, because we have a new interaction, a new term in the Hamiltonian, to wit little a, we have a third diagram, which I can I'll just represent by a cross or something, since I don't have any, it doesn't have any lines on it. It's just the effect of the a term. Its contribution as a connected diagram is simply plus IA, from e to the minus IH. the counter term, A. This one is just equal to either minus IH plus IA. Only diagrams 1 and 3 contribute to the U matrix element between vacuum and vacuum. Their numbers, and their exponential comes into the vacuum to vacuum U matrix element. And by definition, they're supposed to cancel. So the vacuum to vacuum, because the vacuum to vacuum U matrix element is by definition of A equal to 1. Therefore, 1 and 3 cancel completely. Their sum is 0, so it will be the exponential of 0. I write that somewhat symbolically, meaning the operator associated with 1 plus. Okay. This, of course, therefore, if we are interested in calculating the ground state energy, we just have to calculate diagram 1, then we'll fix A, and A is the ground state energy. However, if we are not interested in computing the ground state energy, just computing the S matrix element, we need to compute neither 1 nor 3, since their sum is 0. This is in general what will happen, even if we had a more complicated theory with such a counter term. The total and complete effect of the counter term would be to cancel all Wick diagrams with no external lines. Because sum of all those diagrams precisely makes a phase factor, which by assertion is to be canceled by A. Now, therefore, to get the S matrix, we need only calculate 2. Okay, let's go. Normal ordered exponential. This is, of course, exactly the same as before. Integral d cubed k, 2 pi to the 3 halves, square root of 2 omega k, are now a 4-dimensional Fourier transform for rho of x and t, factors into a 3-dimensional Fourier transform in a 1-dimensional one, since rho is a product, rho of x, f of t. I'm sorry, this is IA. Sorry, I wrote something wrong. Integral bt f of t, of course. We still have to integrate. There's an integral in the exponential. So let's go back to this. Rho twiddle of k, f twiddle of omega k. That's our old rho of k and omega k, which is now a product of 2 terms. AK adjoint, just as before, plus Hermitian conjugate. That's just our old calculation, and of course a colon at the end. That's just our old calculation of last time for a special form of rho of x and t. Well, what does this thing look like? Here I've got f of t sketched. I'll keep it on for a moment, although I'll erase it shortly. F twiddle of omega equals integral d omega. Let's see, I picked up an e to the I kx in the definition of this, so I pick up an e to the minus I omega t in the definition here. Not d omega, dt, forgive me, f of t. Now f is looking like this. That is to say, it is going to the constant function. So for a large t, f of t will approach a delta function, or I guess 2 pi times the delta function. So it's the integral with the 2 pi in the denominator. It gets a delta function, f of omega. Therefore, if I plot f twiddle of omega against omega, will be some very highly peaked function with a spread on the order of 1 over t. and a height on the order of 2 pi t. So the total area will be 2 pi. As t gets larger and larger, this gets narrower and narrower and eventually becomes a delta function concentrated at omega equals 0. 2 pi times the delta function. Now, this has interesting results because it means since omega k is always greater than mu, f twiddle of omega k goes to 0 for any omega k of interest, because it's concentrated at the origin, and eventually 1 over t gets much less than mu. Therefore, this goes to exponential of 0, which is 1, as capital T goes to infinity. That is indeed A unitary matrix, and B, completely free of dependence on capital T. Of course, it's physically rather uninteresting. It says if we have this lump sitting there, then, and we scatter a meson off of it, the meson doesn't scatter. It just goes right on by. This, of course, can be explained in the same more physical words we used to explain the production process last lecture. The mesons interact with the source one at a time. They're either absorbed or emitted one at a time. And if, since the source is time independent, it can't absorb or emit a meson because a time independent source cannot transfer energy. It can only transfer momentum. And a meson always has non-zero energy. In any event, even if you don't understand those words, you should understand the equations on the right-hand board, which says there is no scattering in this case. Well, the S matrix is uninteresting and rather structureless, but still we can compute the ground state energy, and that may be interesting, so let us now turn to that. Let's write down the condition that these two, diagram 1 and diagram 3 cancel. Because you can only absorb and emit a meson one at a time. Your source is time independent, so it has no energy. It can't transfer energy. And since absorbing a meson takes energy, and so does emitting a meson. And since it cannot give up energy, nor can it accept energy, since it is time independent, there's nothing that happens. It's the same argument as this thing vanishes unless rho twiddle of k and omega k is non-zero. Here is an example of a non-zero function whose Fourier transform vanishes on the mass hyperboloid. In fact, vanishes everywhere except for a tiny neighborhood of omega equals 0, which does not include any part of the mass hyperboloid.
But if we had a p-squared term,
then there would be scattering, and maybe I will give you that as a future homework problem. It's not so hard. You've just got to sum up a chain of graphs that look like this. They turn out to be a geometric series. Now, let's write down the equation. 1 and 3 have to cancel. Therefore, I have plus IA integral f of t dt equals whoops, sorry. Yeah. Minus IG quantity squared over 2, which is the 2 from the exponential, 1 over 2 factorial. Integral d cubed x1 dt1, that's writing out the 4-dimensional integral. Integral d cubed x2 dt2, row of x1, row of x2, times, going on, f of t1, f of t2, phi of 4-dimensional x1, phi of 4-dimensional x2. Now, we can write this using our fact that phi of x1, phi of x2 equals integral d4k over 2 pi fourth e to the ik x1 minus x2 dot. I can never remember whether to put a plus or minus sign here, but it doesn't matter because it's an even function. I, and I'll now write things out, omega squared, which is k naught squared, minus k squared, minus mu squared, plus I epsilon. That's just k squared minus mu squared plus I epsilon written out in the space and time components. The integral then becomes, our fundamental equation then becomes integral FIA integral f of t dt. We obtain the x integrals give us a Fourier transform. So I have minus I, gathering together the i's and the minus sign, g squared over 2, integral d cubed k d omega over 2 pi to the fourth. That's just the d4k from up there. 1 over omega squared minus k squared minus mu squared plus I epsilon. A row twiddle of k, quantity squared from the x1 and y1 integration. F twiddle of omega quantity squared from the t1 and t2 integrations. Are there any questions about this computation? It's just straightforward substitution and the definition of the Fourier transform. Now, let us now go to the limit of large T, because that's what we have to do to compute the energy. And am I going to get a sign error? That would be a disaster if I get a sign error. Oh, no, I made a mistake. It's the sum of these two things that's supposed to equal 0, right? This one plus this one equals 0. So there's a minus here, and there's a minus here. I apologize. It's the sum of those two things that are equal to 0, so one is equal to minus another. Now, A, as I say, goes to the ground state energy E naught. Integral dt, f of t, goes to t, dropping terms that do not grow so rapidly with large T. F twiddle of omega, as I say, goes to a delta function normalized near peak near omega equals 0. We still have the drawing down here. So therefore, in the omega integral, we can replace integral d omega, and I'll take out one of those 2 pi's to stick it with the omega. replace omega by omega equals 0, since the whole thing is peaked near omega equals 0. And this is all the omega dependent terms in the integral. So this thing goes to integral d omega over 2 pi f twiddle of omega squared 1 minus 1 over k squared plus mu squared. Once I've set omega equal to 0, I need not worry about the I epsilon, since the denominator then never vanishes in the range of integration. And this integral is, of course, equal to integral dt f of t squared by the famous theorem on Fourier transforms. What is it called? Parseval's theorem? Which we can easily compute just by staring at the drawing of a time still 1 over minus 1 over k squared. Which we can easily compute by staring at the drawing here. F of t is equal to 1 in this enormous region, and therefore its square is also equal to 1 in that enormous region. And then there's a boundary term, which we drop because it doesn't grow with t. So this is simply equal to capital T times minus 1 over k squared. Ha! Bet for a moment you thought I'd get a t squared and would be in trouble, didn't you? Therefore, assembling all of this, and now if everyone is clear as to the approximations I have made, I can erase these drawings and go on to the right-hand board. But if you have questions, ask them now. The t's cancel, the i's cancel, so I get a real energy, which is a relief. And I find the ground state energy is given by the formula. E naught equals minus g squared over 2 integral d cubed k over 2 pi cubed rho twiddle of k quantity squared 1 over k squared plus mu squared. This is, in a sense, the final and complete answer to our problem. It tells us what the ground state energy is, but it's worth a little work to turn this formula from momentum space into position space. The same formula can be written as minus g squared over 2 integral d cubed x d cubed y rho of x, g of x minus y. Did I make a mistake? I hear mumblings. That's right. Well, that's what you expect. There's a general theorem that if you add something to the Hamiltonian that has no expectation value in the unperturbed ground state, then that always lowers the energy. That's a trivial consequence of the variational principle. So if the sign had not come out negative, I would be very disturbed. Since the term we have added is linear in phi and therefore has zero expectation value in the unperturbed ground state. Okay? The g of x minus y, rho of y, and I'll write down the definition of g, and you will see that this formula is just a definition. Integral d cubed k e to the I k dot x minus y over 2 pi cubed 1 over k squared plus mu squared. I write it this way because This is, because I told you that rho of x was some sort of classical version of a, quote, nucleon density, unquote, just like the classical charge distributions that entered in electrostatics. Remember, I called this model quantum mesostatics. And the energy of the system is therefore written in a form that looks very much like the energy of a electrostatic system. Charge distribution at point x, charge distribution at point y, interaction with energy between x and y integrated. The 1/2 is also there in electrostatics. The only difference is, of course, that here there is a minus sign, whereupon in electrostatics there is a plus sign. And therefore, this represents an attractive potential between our infinitesimal elements of nucleonic charge rather than a repulsive one, as in electrostatics. And secondly, of course, this is not the Fourier formula for the function 1 over x minus y, which is the electrostatic 1 over the length x minus y, which is the electrostatic potential, but the Fourier formula for something different. That represents the interaction between two infinitesimal elements of, quote, nucleonic charge, unquote, as opposed to electric charge. Now, do people understand those words? If not, ask questions. Now, what is the interaction between two infinitesimal elements of nucleonic charge? Well, those of you who took my Physics 251 course can probably wake up screaming doing this integral because I arranged matters. It turns out this sort of integral is very useful in doing the hydrogen atom and all sorts of such things. So it came up again and again in 251. But for the benefit of those of you who have missed that golden experience, let's do the integral. Identical in its angular dependence to the integral we did in the first lecture, so I will instantly write out the radial integral. Minus infinity to infinity, dk, k squared dk, doing the angular integral. No, because I take the e to the ikr and the e to the minus ikr and make them plus infinity and minus infinity respect, the plus and negative real axis. E to the ikr, kr from doing the integral, 2 pi from the theta integral, ikr, I'm sorry, from doing the cosine theta integral, 2 pi, the 2 pi cube that was there to begin with, and 1 over k squared plus mu squared. This is from doing the phi integral, and then the theta integral gives me e to the ikr minus e to the minus ikr, which I put together to make a single integral from minus infinity to infinity. As before, the k's cancel. One of the k's cancels. And the integral can easily be done by contours. If I sketch here the complex k-plane and observe that 1 over k squared plus mu squared equals 1 over k plus I mu times 1 over k minus I mu. There are poles at I mu and minus I mu. The original line of integration goes like this. Because r is always positive, I can safely complete the contour of integration in the upper half k-plane, where the exponential decreases unbearably rapidly. And since now all I have in the contour of integration is a single pole, I can evaluate this formula by Cauchy's residue formula, which I proceed to do. G of x equals 2 pi I from Cauchy's residue formula. Two pi squared from being left over inside there. 1 over r left over inside there. 1 over IR, I should say. K evaluated at the pole, which is at plus I mu, gives me I mu. 1 over K plus I mu to evaluate at the pole is 2I mu. And the exponential is e to the minus mu r. As you see, a considerable amount of cancellation occurs. And our final result is 1 over 4 pi e to the minus mu r over r, which is known as the Yukawa potential. Yes, right, we've got the Yukawa potential. Thus, the infinitesimal elements of this imaginary or this thing we have called nucleonic charge density have an interaction energy proportional to a Yukawa potential. Notice the singularity of the Yukawa potential at r equals 0 is the same as the singularity of the Coulomb potential at r equals 0. Of course, the large r behavior is very different. It falls off very rapidly with distance, being essentially negligible when r is several times greater than mu. That is to say, when r is several times than mu inverse. That is to say, when r is several times greater than the Compton wavelength of the meson. The meson, which doesn't scatter, but still is responsible for the force between the elements of nuclear matter. Notice also that if we had rho a point charge, that is to say, if we put in rho equals a delta function, then just as in electrostatics, the energy would be infinite. So let me write that down, since that's an important observation. This divergence is called an ultraviolet divergence. Of course, it's not a serious problem to us because rho is a function under our control, and we need not choose it to be a delta function if we don't want to. It's called an ultraviolet divergence because in K space it corresponds to a blowing up at the integral at the high K end. Because if rho is a delta function, rho twiddle is a constant, and then the integral blows up d cubed k over k squared. Of course, this divergence is nothing to worry about, because if rho need not be a delta function, as I say, it need not be spread out. Nuclear matter need not be an assembly of point particles. And even if it were an assembly of point particles, for some fixed number of them, 7 of them, moving about on little tracks, then the terms coming from the self-energy of each of the particles is totally irrelevant. You cannot measure that energy. It makes no force. It doesn't change as you move the particles apart. The only term that you actually measure is the part that depends on the distance of separation between the particles, the only thing you can adjust, and that part is, of course, perfectly finite if they are at finite distances from each other. Yes, sir?
Is there any reason to disbelieve the answer we get is set mu 0 at the end here?
No, that is the right answer. It would give you a repulsive Coulomb potential, an attractive Coulomb potential rather than repulsive one you normally get. At certain stages in my argument, I was assuming mu is not equal to 0, but that can be refined to include mu equals 0. Yes?
And if we had done it with the phi squared theory, we would have found it out.
At large distances, we'd find, no, I don't think, we'd find a, sorry. We can think of these two elements, the drawing tells us these two elements of rho exchange a particle, if we want to use that kind of language. And the phi squared theory, the simplest thing that could happen to lowest order in perturbation theory is they exchange two particles. This turns out because a two-particle state has is the same as a single particle state, a continuum of single particle states with the mass beginning at 2 mu and going up to infinity. This yields a continuous superposition of Yukawa potentials. with characteristic ranges between 2 mu and infinity. Okay? There are other more complicated diagrams that would correspond to terms with 3 rows in the integral that would be 3-body forces in the sense of nuclear physics, or 4-body forces. Okay. But those are not dominant terms for large separations, as it turns out. They go off like e to the minus 3 mu r and e to the minus 4 mu r if you work things out. You can't see that, but take it on trust. That's what happens. I mean, there is a possibility of 3-body forces in nature. It's only simplicity that makes us restrict ourselves to 2-body forces. Now, it's important, I wanted to emphasize that firstly we get a Yukawa force, secondly we get an ultraviolet divergence if we go to the point particle limit. This may cause us some troubles when we finally get to model 3, where the interaction is psi star psi phi without any integrating functions to smear things out. There are nucleons are not like the nucleons here. They're real particles that can recoil and be produced, but they still definitely interact with the phi field at a single point. And therefore we might or might not, we'll have to wait and see, get an infinite energy shift, which we'll have to worry about. Now, we can also compute not just the ground state energy, but the ground state wave function. This is just an exercise to show you that restricting ourselves to time-dependent perturbation theory is not as restrictive as you might think. We can do all the things we usually do in non-relativistic quantum mechanics with time-independent perturbation theory. And in particular, we can construct the ground state wave function. Remember when we did our table, I see my cough is, am I blowing so much smoke into the room that other people are coughing? Remember when we studied our adiabatic turning on and off, turning on of the interaction, we said that in the large T, large delta limit, u of 0 infinity, that's just getting up to time 0, halfway along the way after the interaction has been turned on, times the bare vacuum equals the physical vacuum times a phase factor, which is of no physical interest. Now, let us consider, this is for anything that's adiabatically turned on, so let's consider f of t equals e to the epsilon t for t less than 0. And as usual, we'll consider the limit epsilon goes to 0 plus. If we also extend f of t for positive t in the following rather discontinuous way, then we can write this as, this of course equivalent to ui because the e to the minus I h naught t makes no difference, and this should be minus infinity. Now we know how to compute that. Indeed, we learned how to compute that last lecture when we were doing problem 1. It's just a somewhat peculiar form of a time-dependent, space-dependent source. Therefore, we can compute it aside from a phase, which is irrelevant, and I won't bother writing down up to phase factors. I don't care how you define the phase of the ground state. relativistically normal. No, I didn't before, so I won't this time. K1 dot 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 Kn, the physical ground state. We might say, that is to say, the expansion of the physical ground state in terms of appropriate wave functions of the non-interacting Hamiltonian, or as we say in our somewhat colorful way, the amplitude for finding n bare mesons in the physical ground state. That's, of course, a stupid way of phrasing things, but it is a traditional one. There are no mesons in the ground state. The ground state just lies there. There are no particles moving around it. But that's the way people use to confuse people to describe the expansion of the ground state of the interacting system in terms of the energy eigenstates of the non-interacting system. Will be, of course, a product, because it's always a product, whatever the form of rho. F of Kn. I'll write down what alpha and F are in a moment. The probability of finding n bare mesons, that is to say, the probability amplitude squared for the physical ground state having a component in the n meson subspace of the for the uninteracting Hamiltonian, is either minus alpha, alpha to the n, over n factorial. And now I've got to figure out what alpha and F are. F of K equals the 1 over 2 pi to the 3/2, rho twiddle of K, something about which we can say nothing, F twiddle of omega. On a sideboard, I will compute what F twiddle of omega is. Integral e to the minus I omega t, e to the epsilon t from minus infinity to 0, dt equals 1 over epsilon minus I omega. And this should be omega k here. A very easy integral to do. And therefore alpha, the key quantity, which is integral d cubed k f twiddle of k squared, f of k squared, I'm sorry, I didn't put any twiddle in that definition, equals integral d cubed k 2 pi cubed 2 omega k. We have seen that object before. And then final, whoops, I left something out, didn't I, here? 1 over square root of 2 omega k. Yeah, that was our formula, remember? These were all the terms that came from the free field. 2 omega k times squaring that thing and setting epsilon to 0, because that's what we're supposed to do. 1 over omega k squared. Rho twiddle of k squared, where I've set epsilon to 0. Are there any questions about the derivation of this formula, where I made several sloppy mistakes that I cured by erasure, so people may have got confused? Okay. Now, something very interesting happens to this expansion of the ground state wave function if we let rho go to a delta function. That is to say, we consider a point particle. It blows up. Not as badly as the energy, but it still blows up. The energy, as you recall, went at high k like d cubed k over k squared. This goes at high k like d cubed k over k cubed. So alpha goes to infinity as rho goes to a delta function. It goes to infinity logarithmically. This integral is logarithmically divergent when I replace rho at the high kn, when I replace rho twiddle by a constant. That is to say, if I have a very, very concentrated source, and I've left out the g. How did people let me make all those mistakes? There's something obviously wrong with this formula, because it doesn't go to 0 as g squared goes to 0. Okay, there it's right. There it's right, finally. Now, but that's irrelevant to what I'm saying now. As rho goes to a delta function, alpha goes to infinity. If you have a very, very concentrated source, and you ask, what is the probability for finding n bare mesons? That is to say, what is the probability that the actual ground state of the theory will have a projection, a non-zero Fourier coefficient in the n bare meson subspace, the n meson subspace of the non-interacting theory. That number gets very, very large as the source gets more and more concentrated. Indeed, it goes to 0 for any fixed n as the source becomes a point. The peak of the Poisson distribution zooms out towards infinity as rho goes to a point in position space, or rho of k goes to a constant in Fourier space. That's sort of disgusting behavior. It's a good thing that in the future we won't worry about computing things like the energy of a difference between the interacting and non-interacting energy of the ground state for a single particle, for a field theory, or a difference between the interacting and non-interacting energy for a single particle, or the amplitude for finding the non-interacting ground state in the interacting ground state. Nobody really should worry about those questions, because in real models, with realistic theories, of course, you don't have the freedom to turn off the interaction. You don't have the freedom to find out what the energy of the electron, one electron state would be if there were no electromagnetic interaction, because although we give ourselves considerable airs at times, we do not have the power to change the electromagnetic interaction, to change the value of the fine structure constant by 1 jot or tittle. Now, fortunately, those things which are physically measurable in this theory, such as the interaction energy between two separated nuclei, two separated point charges, do not display such pathological ultraviolet divergences. So, maybe we'll be lucky. Maybe we can get by with our theory of point particles, even if it does turn out to have all sorts of disgusting infinities in it. Perhaps those infinities won't enter into any physically observable quantities. Perhaps not. We'll have to wait and see. Probably it depends on what the theory is. Sometimes they will, sometimes they won't. We'll see. Now, there's another divergence implicit in this integral, which has nothing to do with what I've been discussing until now, and is perhaps best expressed not by thinking of this as an example of theory 2, expanding the ground state, but as an example of theory 1, where we have just chosen a particular form of f of t, one where we turn things on very slowly and then turn them off abruptly. In this case, this formula has another kind of divergence in it that has nothing to do with the fact of whether rho is spread out in space or not, but has to do with the mass of the meson. This formula blows up unless rho vanishes at k equals 0. As mu goes to 0. Because then omega k is k, and at the low energy end, the integral blows up like d cubed k over k cubed. For obvious reasons, this is called an infrared divergence. Since we will eventually have to confront a series of massless particles that are indeed radiated in interaction processes, in particular we'll have to confront the theory of photons, it is perhaps worth saying a few words about this divergence. This divergence is also unphysical. This says that if we call our massless mesons photons for a moment, abusing language, if we take a source of the form I had on the board, where we build it up slowly and turn it off abruptly, on the average, we radiate an infinite number of photons. That's rather silly. I mean, in a real photon experiment, this isn't a real, far away from being a real photon experiment, but in the real photon experiment, where you sit there with a Cherenkov counter or no, Cherenkov counters are for electrons. How do you detect photons? Yeah. Photomultiplier, yeah. Photomultiplier tube, you never read a report that says we observed an infinite number of counts. Well, the answer is that although an infinite number of photons are radiated in this process, only a finite amount of energy is radiated, because the formula for the expectation value of the energy is integral d cubed k, same old 2 omega k cubed, same old 2 pi cubed, same old g squared, same old row twiddle of k squared, but an extra omega k, as we showed at the beginning of this lecture. So that does not go to an infinite value as mu goes to 0, because that goes at small k, like integral d cubed k over k squared, which is perfectly convergent. What has happened is a sort of Achilles and the tortoise phenomenon. You have a finite amount of energy to distribute, but photons are massless. So you can give increasingly smaller and smaller amounts of energy to each photon. You can give half the energy to one photon, and a quarter the energy to another photon, and an eighth the energy to the third photon, and a 16th of the energy to the fourth photon, and thus distribute a finite amount of energy among an infinite number of photons. Now, this experimental resolution of the process, therefore most of the photons that are of this infinite number, indeed the overwhelming majority of this infinite number, have arbitrarily low energy. That means they have very, very long wavelengths. Now, actual experimental apparatus, a photomultiplier tube or anything else, not just a photomultiplier tube, a radar antenna, however you're detecting your photons, has a low frequency cutoff. The photon is sufficiently soft, if the electromagnetic radiation has sufficiently large wavelength, then you cannot detect it with any finite experimental apparatus. To detect a photon that has a wavelength of 1,000 light years, you need a radar antenna that is 1,000 light years on a side. Those are not found in your average high-energy physics laboratory. Therefore, the reason we got an infinite answer again, even in this extreme limit, is because we were asking an unphysical question. Just as unphysical as what is the expansion of the true ground state in terms of the ground state of the unperturbed Hamiltonian? What would the energy of a point source be if we turned off the interaction? Those were unphysical questions. Here we were asking the question, how many photons would we detect if we had an experimental apparatus that could detect any photon, no matter how long its wavelength? That is an impossible question. If we ask the question, what is the average number of photons we can detect if our experimental apparatus can only detect photons of greater than a certain k, greater than a certain momentum, because it has a finite size, then it is easy to see that in this integral we would not integrate all the way down to 0, but just down to our low energy experimental cutoff. And then even as mu went to infinity, we would not make alpha, even as mu went to 0, alpha would not go to infinity. It would go to a finite value. So once again, saved. It's a real Perils of Pauline story. If we're sloppy and ask unanswerable questions that are empirically unanswerable, we get in extreme limits, but physically reasonable ones, nonsense answers. If we are careful and restrict ourselves only to asking the questions which correspond to experiments we can really do, then we get finite answers, even in those extreme limits. Now, whether that situation will prevail when we go to more complicated theories than the ones we have at hand here is a question that will be resolved only by future investigation, which I will begin next lecture when I will begin tackling Model 3.